No, my friend Mazda working in the launch. Maybe they decided. So how is it going? How's the course going? Any comments? Carol? Anything you want to change?
I do have a
Question.
on homework 7,
Mhm.
number 2,
Mhm.
2A, the omega is not equals to 1 over C, Q, E over M. So, is the C supposed to be C squared?
Dimensionally, you can check it. So your point is, so typically the cyclotron frequency is QE over M. That's the cyclotron frequency. So that's dimension is 1 over time. And alpha is QE over M. That's acceleration. Right? So if you multiply yeah, so magnetic field, remember the Lorentz force is Q times E plus QV cross V. In that sense, the dimension of electric field is equal to dimension of velocity times dimension of magnetic field. So these two should be connected by C, right? Q over M, Q over M, so B and B. So it suggests that alpha should be equal to C times omega, at least dimensionally speaking. And that's why that C is introduced.
Okay.
What was the question?
The question was in the homework 7, problem 2, there is a notation like this, omega, C and alpha, just an introduction. So the question was, is there a C square by any chance there? So I think probably the reason is because MC shows up here. So maybe MC square, you wanted to think of it as energy. Maybe that was
And the relative frequency, there should be a lambda denominator, right?
so again. So this is 1 over. So omega would be 1 over time period, yes. So this is probably what you're saying is this is C over lambda. Is that what it's pointing out?
And I'm just saying that relativistic frequency for relativistic particle, the lambda should be in the denominator, right?
Correct.
Because in order to incorporate the mass, in order to incorporate mass at higher velocities, I kind of worded it wrong, but
Yeah, let me leave it to that problem. Yeah.
yeah, but It's
You have something for me?
Yeah.
I probably need to return something also quickly, I guess. Homework 7 due Tuesday. We have already studied whatever you need for homework 7, so that's good. We will start. I will come back to electromagnetism and do something very simple. We write Maxwell's equations in the language that we have now. We'll make it compact in a sense, but it will bring in the Lorentz covariance in a more explicit way. So that's what we're going to do. So I was bringing out the question, is there anything, this is a good time where we leave relativity and go back to electromagnetism. Anything you guys want to make a comment on about the course? Anything you want to mention? Going too slow, too fast?
Any questions of it now, but maybe in the future.
So keep going as we are going, right?
Yeah.
Okay. So remember, in the most of relativity, what we have said is that there are 4 vectors. If we can recognize 4 vectors, it is convenient because the Minkowski length of that quantity remains the same in every frame. So it's not appropriate to talk about length, time, or any component of a 4 vector. It's the Minkowski length of a 4 vector that should be dealt with, which and we did go into kinematics and then talked about what's the 4 velocity associated with the velocity itself, what's the 4 vector associated with acceleration, what's the 4 vector associated with energy momentum. And then the natural question is, when we are doing electrodynamics, where does all the electric field fit in? Where is the current? Where is the current density? There's a lot of quantities that we introduced in electrodynamics, Maxwell's equations for that matter. How do they transform? How does electric field and magnetic field transform? Especially magnetic field is very, it should be curious. For example, if there is a particle that's moving with velocity v, it will create a magnetic field. Is that clear? So this will create a magnetic field. This is like a current here, so it should create a magnetic field in this sense, right? So that should be the magnetic field it will create, and it will be weaker in the front, weaker in the back, but there will be magnetic fields it will create around it. But the moment you go in a frame where the velocity is 0, that magnetic field disappears. So it's very clear that magnetic field in that sense is relative. It goes from 0 all the way to finite quantity. And then you say, how does magnetic field transform? And it will turn out that it does not transform like a 4 vector at all. It's not a vector, but it transforms like a tensor. And those are the things we want to deal with. Remember, maybe digression again, how do we define a vector in general? The usual vector, how would you define it?
Direction.
Magnitude and direction, yes, but something more formal maybe? For example, if it's a magnitude and direction, is electric field a vector in under Lorentz transformations? It's not a vector. Right? For example, space vector is a component of a 4 vector. So it seems like there is something more general we are talking about here. So in what sense is, so what is a vector? So again, you were trying to answer something.
We need the basis.
You mean I, J, and K? Yes, sure. But that's the same as magnitude and direction, right? So for example, when I say that electric field is not a vector under Lorentz transformation, what does that mean? Yeah, so maybe we should make this more concrete a little bit. So when we say when we say the usual vector that we talk about before we have come into Lorentz transformation, this is with respect to rotations. So what are rotations? So think of any 3 quantities, A1, A2, A3. It could be anything. Typically, these are the 3 components of a vector. But any 3 components that transform the same way as a position vector transforms under rotation will be a vector. There is a very specific way the position vector X, Y, and Z transform under rotation. If you can do a 1-to-1 mapping between any 3 quantities, think of a function which does exactly the same thing under rotations as a position vector, then that's a vector. So that's a strict definition for a vector. What do I mean by something is not a vector under Lorentz transformation? The same quantity now we take, say, is under Lorentz transformation. So 4 vector is with Lorentz transformations. Like it's a 3+1 dimensional transformation. There is a boost and a rotation. And now we are talking about 4 pieces. 4 objects which transform under Lorentz transformation exactly like the position 4 vector does. That's a Lorentz 4 vector. So something that is a vector under rotations need not be a vector under Lorentz transformation. There are 2 different definitions. Is that clear what I meant there? Very briefly, at least conceptually. So, or maybe the point is any vector is always associated to a transformation. You can always have vectors with different transformations. In principle, any, but mostly vector is associated with something that has a magnitude and that doesn't change. So under rotations, the magnitude of the vector doesn't change. Under Lorentz transformation, the magnitude. So we usually associate a magnitude and direction also with a vector. So due to that reason, for it probably may not be very popular to say that under any transformation, but at some generalization level, you can do that, and that should be okay. Okay, so with that as our so that was the idea of a vector and a 4 vector. And once you have a vector, you can, so this is the same as AI, right? Or under like superscript or subscript. And we can immediately talk about tensors, right? I and J. What is a tensor? Any 9 components that transform like 2 position vectors. But they should transform exactly like a normal tensor does. This will be a 4x4, 16 components doing the same thing. So the idea of a tensor and a vector immediately generalizes from rotations to to Lorentz transformation, and we will see that electric and magnetic field are going to be tensors. And then the Lorentz transformation properties will be of interest. So let's talk about Maxwell's equations then. So we want to talk about Maxwell's equation, how they look like. So that's a background. Let's remember what does Maxwell's equation have? That is charge density, rho. Then there is current density, J. Those are the quantities that Maxwell's equations are involved with. There is also the electric potential phi. That is the magnetic vector potential A. All these are familiar notations. I don't have to redo that, right? Familiar, mass?
The third one, that's flux. Right?
That's the electric potential that we typically say V. In undergraduate physics, we say V, but here we are going to use phi. That's more standard and higher advanced physics. It's for some reason phi.
And that's the first one, charge density.
That's charge density, current density, electric potential, magnetic potential, like maybe writing it this way helps. Electric field is equal to, in terms of electric potential, what's the definition? What's the electric field in terms of electric potential? Minus gradient of, very good, of phi. And magnetic field in terms of vector potential. Very close to J. Spell it again.
Curl of A.
Curl of A, right? Yeah. Is there anything missing in all this? Something is wrong or missing?
For E, we have the time derivative of A.
Very good. This is only for statics. Only in electrostatics we do this. When dynamics comes into picture, this is not sufficient. There is a time derivative of the vector potential with respect to time. So that's the connection, and we have electric and magnetic field, right? That works. So Maxwell's equations deals with so many quantities. All these are, when I say the vector sign on top of it, it means vectors under rotations. Right? These are not four vectors or four tensors. But now Maxwell's equations, of course, like that's your definitions if you want, and the Maxwell's equations are divergence of epsilon naught times the electric field is equal to charge density. So dotted with B is equal to 0. Del crossed with E and plus.
What did you say A was again? It was the
It's a magnetic vector potential.
Okay, magnetic.
I think of it, yeah, magnetic potential, you can say. This is the scalar potential. Derivative of that gives you the electric field. Here it is a curl of that, so it's a vector quantity that gives you that. So magnetostatics will be done in terms of A, like when we do magnetostatics, which one spends a lot of time on, then it is done in that. And the time derivative plays a very little role in Faraday. Faraday induction problem, but again, that is done in terms, often it is done at the electric and magnetic field level, not in terms of the electric potential and magnetic potential. And there's one more equation, and that's del cross with H minus E epsilon E over dt is equal to J. And maybe you can write this in terms of B. It's B over mu naught, but that's one way of writing it. That's it. That's a Maxwell's equation. You've seen it many times, but here is how we will begin our construction of four vectors in a sense. So let's say this will be four potential. So four vector potential. Notice there is an electric potential and a magnetic potential. As a good reason to put it together, and we will say that they will be a, which one is this, up or down? A mu is equal to phi over c, and that's your free component. This is where every book will be different. Sometimes you write your C here, C there, so there are various ways you can write this. Remember, special relativity can be done in different metrics, plus or minus, so there will be significant differences when you look into books. So usually it is a sign that changes, the overall idea remains the same, that the zero component of the four vector is your electric potential, and the spatial components of the four potential is your magnetic vector potential. Right? So if you want, this is a definition if you want, right? We begin with a combination of phi and A, that is all we can do. Let's next do for tensor. So let's say field tensor. Maybe before that, I should say, just to clarify, and that should give you some practice on this. A mu would be equal a, that's a contravariant, the covariant vector associated with the vector potential will be just the time piece is changed, right? It is made minus. And this remains the same. Is that clear? So that's straight forward. And next, let's define what is called a field tensor, electromagnetic field tensor. Maybe I should say it's electromagnetic, right? So this is electromagnetic. Often you don't say the word electromagnetic, but it's understood that it's an electromagnetic field tensor. So that will be defined as F mu nu, two indices. That means it's a tensor, right? Whenever there are two indices, you think of it as a transform. It will transform like a tensor. This will be the 4 derivative times a nu minus of d nu times a mu. So it's a, and maybe we haven't used the 4 derivative so much, so that's 4 derivative, maybe 4 gradient, maybe 4 gradient of 4 derivative is d mu is equal to 1 over c d by dt, and this is the gradient. Notice it is the covariant component, or the downstairs component is what is chosen as a positive. If I make it upstairs, this will be minus 1 over c d by dt. Whenever I go up or down, the time component switches sign. That's our understanding. And this is the definition of the field tensor in terms of a nu. And the claim is whenever you have this derivatives, you have this electric and magnetic field. So we're practically defining electric field and magnetic field, whatever was here in terms of this quantity. But how do we see that? Let's see it more closely. Any questions? Yeah.
Minus can be done just because of it for the time, like time part. Minus normally is it in the other way, right?
If it is a, so this is how it goes. Position is usually the positive. The gradient will always be the opposite. And why is that? Because you always want the mu times, let's say, x nu should be delta mu nu. This is the generalization of we have been using. Remember, this was r that was equal to 1. In 4 vector, you want to generalize this, and so you write it in such a way that it always will give you that 1. If you keep both up, it won't be 1, then it will be a metric that it will lead you to. But that's perfectly fine. But if you choose it like this, then you do. Somewhere you'll choose a position. Typically, I think again, maybe mostly standard. Most of the books that I'm aware of does this, that the position is upstairs, a contravariant position is chosen positive, and a covariant derivative is chosen positive. So that together they come in.
Okay.
But if you switch both, then you good. So it's a choice.
Okay.
Okay, with all that, let's see what we have. So we have defined our 4 vector potential. We have some tools, which is the 4 gradient question. Yeah.
Is d mu the same as d nu?
Oh, yes, remember del I or del J, these are just some letters, right? But once you have I, then it becomes a free index. If you're writing an equation, right side also should be the same. So I just chose mu. Remember, we have been using Greek letters for running from 0, 1, 2, 3, 4, and IJKs for or Latin letters for spatial components. So I could have chosen mu here or alpha here, beta here, anything. So that the free index, if I write something on the right side with an index, then I will be consistent. Otherwise, I can pick anything. And this means that there are 2 free indices here. Right? Mu is also free, nu is also free, correct? Okay. What is F nu mu? If F mu nu is that, what is F nu mu equal to? So I will say this is d nu, just by definition, right? I'm flipping mu and nu. That's minus d mu a nu, which is exactly flipped. So that's minus of F mu nu. So if you think of this as a matrix, these are 16 components sitting here, right? If you think write it as in the form of a matrix, there are 16 components, and what will happen to the diagonal elements if I say that F mu nu is equal to F nu mu? What happens to the diagonal elements?
Same.
They are the same. No, something more.
Complete.
Huh?
Complete.
No, I'm saying that you have a matrix A, B, C, D, keep it complex, right? And I'm saying when I flip it, this is like interchanging. So this is transpose of this. this has to be equal to, so let's say. A, B, C, D. But these are exactly negative of that quantity. Right, so what we are saying is that A is equal to minus A. Right, isn't that what we say? So
Capital A is equal to minus
capital A is equal to,
A.
right, minus A, okay, same thing. Capital A is equal to minus A. And help me here. But we are saying it is exactly the same to begin with, right? So we are trying to say that this is equal to minus A minus B minus C minus D, correct? Isn't that what we're saying? The transpose of this is exactly the same, which means that A has to be equal to minus A. So when can you have A and minus A the same?
0.
0, right? So what we're saying, so this is like anti-symmetry, right? Maybe I don't know whether I said this correct or not. But if you have an anti-symmetric matrix, its transpose is exactly the negative of that, and that also requires that the diagonal elements will be 0. So just by construction, like this is a way of constructing an anti-symmetric tensor. So this means that this is anti-symmetric. Anti-symmetric in what sense? Anti-symmetric under change of indices. If I change mu and nu, my components will all flip sign. That's all it means. It's anti-symmetric in the flipping of mu and nu, or swapping of mu and nu. So that's good. So we immediately know that f 0, 0 is 0. So if I ever ask you what is f 0, 0, that's equal to 0 immediately. Right? Just because it's anti-symmetric, it cannot be there. So we, out of the 16 components, how many are independent then? If I tell that there is an anti-symmetric matrix, 4 by 4, how many are independent?
Six.
Right? 6 of them. So I have 1, 2, 3, 4, 1, 2, 3, 4, 4, 1, 2, 3, 4. These are all zeros now, gone. But these are the same as this, except that they're negative. Right? When I transpose it, I get a negative sign. So these are not independent. So this is the only independent one. And as Aryan pointed out, so there are 6 of them. Right, so there are 6 independent components in this. Is that clear? Okay, just because of anti-symmetry, the way I have constructed it, there are only 6 independent components. Any questions on that? Not satisfied.
So if we want to so if you were to increase the matrix size, it'll only.
Oh, yes, if it was not 4 by 4, but remember mu nu are space-time indices here, right? So it is 0, 1, 2, 3. Right? So yes, you're correct that if it was 5 by 5, then it is different. How much is that? So if it is 5 by 5, it is 4 plus 3 plus no, 4 plus 1, 2, 3, 4. Okay. Yeah, 4 plus 3 plus 2 plus 1. Right, 7, 8, 9, 10 of them. So then it will be 10 pieces in there. If it was 4 plus 1 dimensions, or just 5-dimensional space time, if you were doing then and that is done in general, but we are not. We are in 3 plus 1 space time. Okay, so that's just some information on that. So again, since you had there was some issue with that, so say this is F00, F01, F02, F03. That's what we will do, right? That's your components of this matrix. If I were to write this specifically, so this is 1, 1, F1, 2, F13, F20, F21, F22, F23, F30, F31, F32, F33. Okay. Notice this is 0. That's 0. That is 0. That is 0. Okay. This piece here, we will call it conveniently F0I. 1, 2, 3. I is the Latin index there. So there are 3 components of and the 0th component here. This one here, we will say is F0, which will be related because these are antisymmetric. F0I is the same as Fi0, right? Or minus of that. Is that clear? And then we are left out with 6 more which are related. This is your, if you play chess, this is like the move of a
Horse.
horse. Yeah, we call it horse, but it's what's that terminology? Rook,
The knight.
knight. Yeah, knight. Yeah. So the knight will move in this fashion, right? So that's also there are 3 components, right? So that's a room for your vector sign here. And with this one, we will call it Fij. Right? Notice I and J are spatial indices. So it runs from 1 to 3, 1 to 3. There should be 9 of them, but that's your 3. These 3 are 0, and this is the rest of the 3. Is that clear? And there will be meaning here. What we are going to show is that this is electric field, and that's magnetic field. That's how it's going to show. Okay, that's how.
So F0 is the magnetic.
Is electric field. So except for some signs and plus or minus. So this will be related to electric field. And Fij will be having the magnetic field in it. But we have to show that. I'm going to show that in the next 10 or half an hour.
Fi0 is also.
Fi0, once you know this is also except for a sign, right? That's why I don't write the sign here. And there are factors of C sitting here and there. So we will see that in a few minutes. Okay. Okay, so that's the definition. Let's start with F0. So I'm suggesting that, oh, this might be the electric field. Well, let's see what it is. So F0I is equal, to start from the definition. So that's the time derivative, 0 derivative. This is I minus Pi a 0. Is that clear? That's 0 I is, that's a definition, right? Just barely I substituted mu and nu in there. But 0 is as far as the 0th derivative, 0th component of the derivative goes, that's 1 over c d by dt. So that's equal to 1 over c d by dt. And this is your magnetic vector potential. Right? Think of it as a vector. So I'm going to, since I have the index on the left, I want to keep the index here, but start thinking of this as a vector from now on, right? That's a vector, right? That's it. This is a right side is a vector, but I have not put the left side, but this is just for our convenience that I put in there. So this will also become a vector in a minute. Okay. Minus, this is nothing but the gradient operator. Again, I keep I there, but now I introduce a vector sign also. A0 was we defined here, right? A0, it is the downstairs version, covariant version. So I have to read this, so it's minus pi over c. So I put the minus pi over c. Okay, with me? Is that clear what I did?
One more time, please.
Okay. Zeroth component is d0, I go and search here, right? That's a zeroth component, the downstairs version, so it's time derivative. With the c, I put that. Ith component, go here, the downstairs version, that's here vector a. And the I here are the three components of it. Go here, derivative, ith component, derivative downstairs ith component is a gradient. That's a gradient. And the zeroth component of the 4 vector A downstairs, that's your minus pi. So that's a scalar potential that is showing up. And that's here. And there are some signs that we have to take care of. With me?
Okay.
Right. So this is nothing but 1 over c. That is a 1 over c on both sides. And that's time derivative of a, the ith component of a if you want, and plus the gradient of phi. Okay. This is nothing but this, right? That's your electric field. That's the way electric field is defined in electrodynamics, except for the sign is missing. So we put in the sign and you recognize that this is nothing but 1 over c times the electric field, the covariant part of it, like the downstairs version of the electric field. But these are all spatial pieces. Remember, I and j are spatial components. Whether I go up or down, it doesn't change sign. It is only the time components that we have to worry about changing sign. Like here, if I were to make this I go up, I don't lose the sign. Is that clear?
You can make the I go up from 1 to 3.
As far as it is 1, 2, 3, no problem. If I change 0 up, then it gains a sign. All right. Every flip, the 0th component flips the sign. 1, 2, 3 doesn't matter. Okay, that's the rule we are having. That's a Lorentz transformation. Or that's this up and down rule if you want. It's a contravariant and covariant. It works better if you have the full metric in hand. Then you can explicitly see this, but that is all we are doing here. 0th component going up and down, change sign.
Okay.
Okay. Good. Okay, any other questions? So that's your electric field. So immediately I know one more thing. What is Fi0? Okay, that's this one. What is Fi0? Yes. Plus, right? I just had it's an antisymmetric quantity. I don't have to redo this. So this is 1 over c times the electric field component. Remember again, this is the x component, y component, z component, right? That's a notation there, right? First one is x, second one is y, third one is. This is all in rectangular coordinates. These are not in spherical basis. This is all rectangular. We have assumed that this is a basis independent, or we are fixing the basis to be the rectangular coordinates. That's another game altogether that we want to talk in terms of other bases. We are working only in rectangular coordinates. So we have identified the electric field sits somewhere in here. What about the magnetic field, right? The claim is that magnetic field is somewhere here in this. So let's see that. Yeah. So Fij, right? Fij will be this 3 by 3 matrix because I and J run only from 1 to 3. So 0 is excluded, that's the 3 by 3, and we're mostly interested in the top one, but it is antisymmetric, it is all taken care of. Okay, Fij is the Aj minus of the J the I. Okay. What is that equal to? Can you say anything about the magnetic field there? It's not obvious, right? How is the mag?
The same as curl of A.
That's the same as curl of A, is it? Like curl is typically a vector, right? One index. This seems to have two indices, right? So there's something we have to do. We need a little processing needed there. But that's a good recognition that yeah, curl of a quantity usually is, but there is an epsilon ijk that sits with it, right? So we want to somehow combine that with this. So instead of going from here to the curl, let's come from the curl to this, right? That's one way of doing it. No, there's nothing wrong in going either way, but let's do it. So let's go back and recollect what is our magnetic field. B is equal to del cross A, right? That's a vector, right? But this is a tensor, there are two indices there. So how are we going to connect that? So remember our index notation. I can be up or down when I'm working in spatial components. So let's say this is K. That's equal to epsilon K I J gradient of I J. So familiar till now? Like this was all done in the first couple of weeks of index notation, but hopefully this work. This is the curl of a curl operation can be coded in terms of Lewis-Evita symbol. But still, this is not the same as this. Right? So, but if I were to move this epsilon to the left, I have some room there. So how do you do that? So let me multiply both sides by actually since this is ij and I'm just beginning, I can write any index there. Let me write that as mn. Just because this one is in terms of ij, I want to read that ij free. I want to multiply this with ijk and bk. So what have I done? I took a k, multiplied it by a tensor, 3 tensor, contracted one of them, so I'm left with a 2 tensor, right? This quantity is a tensor and I and j, k is summed up. Clear? I will do the same thing on the right side. So that's epsilon I j k, epsilon k mn, gradient m n. Good thing. This is something we talked about. This was this can be written in terms of Kronecker delta. I can move k 2 times, and this is nothing but delta I m delta j n minus of delta I n delta j m. Write 1 and then flip it, and you have delta m. Expand this out. Like remember Kronecker delta, when you sum over or contract, it just swallows one of the indices and you get del I aj minus del j ai, which is exactly what we have here, which means to say that Fij is equal to the, So this is like cyclic, right? 1, 2 component will be the third one. Is equal to epsilon I j k. You see this in angular momentum also, right? Times P of k. Okay. So what is let's say F, that is F1, 2, right? So F1, 2 will be epsilon 1, 2, 3. Once you have chosen 1 and 2, there's only 3 remaining. Right? So there's only 3 remaining, so that's P of 3, that's equal to B3. F1, 3 is equal to epsilon 1, 3, 2, B2, but this is not cyclic, that's a minus sign there, that's minus B2. And F2, 3 is equal to epsilon 2, 3, 1, B1, that's equal to B1. So what is your F mu nu in all together? You have F mu nu, we have got everything now. Notice it's important that they all stay down. If you move it up, then all these signs can change. So this is equal to 0. And let me put C here. Multiply out by C. And this is E1, E2, E3. This is minus E1, 0. That is minus E2. And this is B3. This is equal to minus E1 minus B2. That's 0. And then that is B1. That's 0. And this is minus B3, B2 minus B1. That's your F mu nu. Oh, so there should be a C there. C here. C minus C. I multiplied it by C just so that the fraction takes more space. Right? Just try to saving in a sense, or it's a little more less clutter. I think that's what I think. That's your F mu nu, and suddenly you see the structure of the tensor that contains electric and magnetic field come up. Notice electric field is here. And the magnetic field is in an upside way manner, sitting here. If you ever did the angular momentum operations, you will always see that angular momentum also comes and sits like this. If you do the infinitesimal transformation, the generators of angular momentum exactly has this structure in it. And that's primarily because it's a cross product, right? J cross J. In quantum mechanics is contained in J. So that's your F mu nu. Okay. So, but Maxwell's equations are mostly vector equations, right? This is a vector equation. That's a vector equation, and that's a scalar. So Maxwell's equation probably is a vector, so this is a tensor. So if I contract it, maybe I'll get the Maxwell's equation, right? So let's try that. So how do I contract it? And notice these are all gradients, right? So let's do the following. Let's try now, or before that actually, what will be C F mu nu?
Wouldn't this sign change?
Yeah, sign of which ones will change?
The E1, E2,
E3.
E3, or E3. Also this, the as well. This for anything besides 0.
No, remember, it's only the time pieces that change, right? So in these cases, there are no times, so this will stay intact.
Just to be.
So on the what?
And if this was not zero, this will also not change sign because there are two time components in it. Two signs going up and down. Right, but this is zero, so we don't care, but this one has only one time component. Like the second is a space component, so that changes sign. So C mu will be 0 minus E1 minus E2 minus E3. Is that clear how I argued that? And one might argue, oh, should I be writing this one up or down because I moved this up? But space doesn't care, right? Space indices doesn't care whether I do it up or down. And this is Z0 C B3. This remains the same. Is that clear?
Now the minus.
Okay, so this one is F
I see the.
F0I, right? The top one, right? F0I is the same as F0I, right? I can move the space pieces up and down, nothing happens. But now if I move the zero down, I pay a price, I change the sign. So this is equal to minus F0I.
Yeah.
F0I was minus electric field. So this is equal to minus of a minus 1 over C EI. That's equal to plus EI, that's what I wrote. Right, and yeah, this is because C is multiplied. Is that clear? Same thing with Fi0. The same idea will go through.
With the minus. Okay.
And that leads to the question that what about F mu nu? What is that equal to? One is up and a down, that's your quiz. And what about F mu nu? That's quiz. Right, just a bit exercise.
That's just.
Yeah, so just write this down and then move it up or down. Whenever needed. Is the question very clear? Like that should be a good exercise to play around with indices. Oh. Let me see. How do I want to contrast? Yeah. So now that I have this contravariant field tensor, let me do the following. Let's do d mu F mu nu. You're asking what is that equal to? Will this be a vector or a tensor or a scalar? Will it be a 3 Lorentz tensor? Will it be a 2 Lorentz tensor? Or will it be a 1 Lorentz vector in the sense of one rank tensor, or is it a scalar? It's a vector because there's only one index, right? The other is summed over, so it's basically a Lorentz vector. Whatever it will give me, is going to be a Lorentz vector, and the question is, what is that equal to? Since it's a Lorentz vector, let's and yeah. And the free index is new, right? So how do I write that? So let's say this is a box and then the new. And that box new. Let's say new is equal to 0. Let me not create all those symbols. I think it's not necessary. Let's say new is equal to 0. Then the mu f mu 0 is equal to, that is a summation over mu. So this is d0 f0 0 plus the Latin indices di fi 0. Okay. What is f0 0? 0, because it's the diagonal piece, that's equal to 0. Plus, this is the gradient Li fi 0 upstairs. Fi 0 is basically minus electric field, right? So this is f0 I. Well, this fi 0 would be minus of 1 over c electric field. That's nothing but minus 1 over c divergence of the electric field. Use the Maxwell's equation. Del dotted with E is equal to minus 1 over C rho over epsilon naught.
How is the expansion?
Tell it again.
The first expansion.
Oh, this one.
Yeah.
This is a summation index. Whenever I have an index repeating, it means it is summed over.
Yeah.
And it is summed from 0, 1, 2, 3. This is the 0. And the I runs from 1 to 3.
I mean, like the time and the space component.
Correct. Remember, our notation was alpha means 0, 1, 2, 3. And Latin indices means 1, 2, 3. So I runs only from 3. So I separated the time and space so that I don't have to write too many pieces in there. Okay. Let me do a little bit more processing. Let me put a mu naught here and a mu naught in there. So that's equal. And epsilon naught mu naught is c squared. So that's equal to mu naught times c times rho. Just a way of writing it. Okay. That's your first Maxwell's equation. Like the zero component of this equation, if I recognize my right side, is my first Maxwell's equation. Nothing new in it. It's just written in a Lorentz covariant form. Absolutely nothing new in it. Physics remains the same, cannot change, right? Just because I used some fancy notation to write it. It
Just
doesn't.
multiplying by 1.
Hmm?
You're just multiplying by 1. You're not over E minus.
And you're multiplying by 1. What does that mean?
Well, I was just saying, because you're taking mu naught over mu naught, which is.
Oh, yeah, so that's just multiplying by 1, nothing can change in that. Yes, exactly. Yeah. And it's okay to leave it here, but I want to keep some generality in that and write that. So I want to identify what the right side is basically. The zeroth component is rho. Now we know, but I want to see what is the other components. Yes.
If the C is the speed of light,
Yeah, C is the speed of light,
No,
right?
in the result, the final one.
Yes. Isn't it? Because 1/epsilon naught mu naught is equal to C square, right?
Oh, okay.
So I will put a C square that one of the C cancels out, so that the mu naught C that shows up. Okay. Let's next put nu equal to I. Right, like I 1, 2, 3, but I'm going to do it in a single soup. D mu F mu I is equal to again do the same thing, summation. So this is D0 F0 I plus DJ FJI. F0 I we said was F0 I was 1/C electric field. So or help me here. So D0 is 1/C time derivative. And that's nothing but electric field. So that's 1/C electric field. I d by dt that's somewhere here, right? So that's probably the equation we are working with. And this one is plus del J. So let's write it as gradient. So that's gradient J epsilon J I K and dk.
So why did you get the J from?
This is a summation, J is 0, 0. And then 1, 1, 2, 2, 3. This is nothing but the magnetic field, right? Those are the inside part in here. That was the magnetic field. We did that somewhere underneath this layer of dust, right? So this is this. Now we rewrite this again. Now let me move this I here so that I can see it as a cross product. This is equal to 1/C square. So that helps me write this as epsilon naught mu naught. Why am I bringing in epsilon naught mu naught? Or first, let me bring it for a moment, right? Epsilon naught mu naught, right? Then dE by dt. And minus, right? Because I and J I'm going to flip. So this is I, J, K, del J, dk. Or IJK and BK I can go up or down, it doesn't matter. So that's my cross product. And there is no epsilon for mu's in there. And what did I do? So pull the mu naught out. Pull the mu naught out and then write this as epsilon naught dE by dt. Actually, pull the minus sign also out. Minus plus del cross B, but I pulled out a mu, so I had to put in a mu naught there. And this is the ith component of this, right? The ith component. Okay. which is exactly the left-hand side down here. And there is a j. So this is equal to minus mu naught times j. And this was I, so this is your I. Oh, the minus sign, help me. No, that's right. Okay, good. So what we have is quickly. So F d mu F mu nu is equal to minus mu naught times C times rho when mu is equal to 0. And this is equal to minus mu naught times j I when mu is equal to I. That tells us that this should be a 4 component, a 4 vector. So write it as minus mu naught j nu, where j nu is equal to C times rho. That's a time component. And the current density is the space components of that. Okay. Often this is written as d mu, flip the sign here, mu is equal to mu naught j nu. Right, that's your Maxwell's equation in index notation. Or the 4 index notation. The notations we have used is current density, the 6 pieces that we were talking about. J mu is equal to C rho times J. A mu is equal to phi over C times A. And electric field and magnetic field is given in terms of F mu nu, and that is the electric and magnetic fields. So you cannot write that here, that's the 4 concept. This is your Lorentz current vector, Lorentz 4 potential, and this is the field tensor, electric field and magnetic field. I'll stop here. There is a talk on neural networks in the math department today at 2 o'clock in 15 minutes. And it is, if you have heard about Chat GPT. So I don't think that's going to address that, but this is the same ideas that are used, basically machine learning, what is popular as deep learning, or what are the words used? Data. What is that? What? Data science? Data science, right? Math, you might be able to talk.
Yeah, data science, machine learning, AI.
Yeah, oh yeah, AI.
Yeah,
I think, yeah, artificial intelligence, whatever we typically associate artificial intelligence with the more recent technologies, these ideas are very much in there. It's in the math department, it's at 386. NECA's 386. And if you're interested in such things,
Who was giving the talk?
Maz's father.
Oh, yeah.
he didn't know. So, yes.
Well, he teaches, he's teaching neural networks this semester, so I gave him.
Yeah. But some of you guys are involved, expected to be working in that, right? Who is working with Siva? Who is working with Siva? I know that you guys are. Are you guys expected to be doing? Data. Processing data? No. Okay, it's okay, no one. I was extrapolating. Speculating. Shall I disconnect this? I need to take it with me.
Okay.
Yeah. So you switched it off, right?
No, no.
Oh. Can you do that from there? Because. Thank you.
So I can find